compute the definite integral from 1 to 2, x squared plus 5x plus 1 over x squared plus 1 with respect to x. Now, we have a rational function in the integrand. The degree of the numerator equals the degree of the denominator. So we'll need to long divide before we can determine what technique we use. In this case, our answer will have a logarithm. Now, before we do our work, let's approximate our definite integral using a Riemann sum. So, what does this definite integral represent? We'll have the net area between the graph of our function and the x-axis between 1 and 2. With a Riemann sum, we're just going to approximate that area using rectangles. So, we're going to take base length of our rectangle equal to 0.01. We note the height of each rectangle is going to be given by our function evaluated at a point. The area of that rectangle is just base times height, and then we sum. So, if I code this into a computer, then I'll get, for our Riemann sum, 3.323. So when we get our precise answer here, we have a check on our work. Now, let's see what we have. First, I have to do the long division. So I'm going to divide x squared plus 5x plus 1 by x squared plus 1. When we work that out, I get 1 plus 5x over x squared plus 1. So that's my new integrand. Now, this first part, okay, there's no work to really do there, so I'm just going to split that off. What's left over, we have to stare at for a little bit to decide what technique we use. Now you'll note, if I take the derivative of the denominator, okay, we get 2x, so that means the numerator is just a multiple of that. If I have a derivative over the function, then the substitution we want to use is u equal to our function in the denominator. So we'll let u be equal to x squared plus 1, du equals 2x dx, and I can solve for dx. Now here, rather than go back to x when we get our answer, let's just put our limits in terms of u. So I'll have that u of 2 is equal to 5, okay, 4 plus 1. U of 1 is 1 plus 1, which is 2. We substitute, so we get this new definite integral here. And we're going to evaluate this using the first fundamental theorem of calculus. So we find an antiderivative, we evaluate the antiderivative at the limits, and then we take the difference. Now the antiderivative of du over u is going to be natural log of absolute value of u. So here what we're going to do is evaluate at 5, evaluate at 2, take the difference to get to here. I could drop the absolute value sign since 5 and 2 are positive. Then we have a log rule which says if I have a difference of logs, then I could just put things together by dividing. So this is going to go to natural log of 5 over 2. So we get our answer to be 1 plus 5 halves, natural log 5 over 2. I punch that into a calculator. We get 3.29, and we see that that's going to be in the ballpark of what we got with our Riemann sum, so our work checks out.